So today let's start from exercise 2.8.6. So based on the description of the theorem, I think it's to say that for any repeating decimal or non-terminating repetition of p minus 1, there exists a representation without having to use that repetition. So I think one way to approach this is to demonstrate that for every x which can be represented as a repeating decimal with p minus 1s, it can also be represented with without the use of this repetition and still be represented in this form. So we can begin with that. So of course then we might make a few observations, one of which is that, well, when does the repetition start? So assume that x equals to this representation where ai equals to p minus 1 repeating for after some index I, and then we can consider that well, what comes after this I index adds up to 1 of let's say ai minus 1 times p to the minus I minus 1. So I think that's one way to approach this. But of course, like you can also do this more precisely by finding the maximum index I, such that ai is not p minus 1, just to define where the repetition starts more precisely. You can also do that. So let's begin. Okay, so how did I enumerate text? Yeah, okay, that's fine. let me look around at some other parts of the definition and see what I can find. So this doesn't have to happen. So the first thing maybe I want to know is there's always some integer n such that x is between n and n plus 1, and specifically that it has to be less than n plus 1. So when you subtract off the remaining portion, I guess the decimal portion of it must be less than 1. And from there we can work with the decimal portion. But I have to find where that claim is originally. I think that's going to be my plan for now, is to show that first the decimal portion is less than 1, and then show that if it's less than 1, then there's no need to repeat any decimals. In fact, I think the second part is kind of like the first part, I guess. I think that's a pretty reasonable plan, but let's just delete it for now. Maybe I don't need this. The way I think about it is, if it's a positive real, then there must exist a least natural which is greater than that real. Well, because of the well-orderedness of naturals. But of course you have to consider that there exists a natural which is greater than any real. which I think is not so easy. Maybe it's not so easy. I don't know how you would do that. I guess probably by definition of the reals. I have to think about it. Oh, because there is at least upper bound, I guess. No, that doesn't say anything. Yeah, it's this. We suppose there's a unique. Oh, yeah, okay, so existence. Okay, they use the Archimedean property. Oh, yeah, I guess the Archimedean property already is assumed, is it? No, it's demonstrated. Okay. Oh, it's trying to use a set that contains multiples of A, natural multiples of A, and they're showing that since it's a set of real numbers, it must have at least upper bound, and that least upper bound is less than or equal to B, maybe. No, what is this? It's arbitrary. Okay. Oh, this is super weird. Okay. I don't quite understand. M plus 1 is in the natural, so M plus 1 times A is in the set. Okay, makes sense. MA plus A is less than the least upper bound. Okay. Oh. Yeah, okay, I see. Because M is arbitrary, which means that every element in the set is less than this, which doesn't make sense because this is supposed to be the least upper bound. Oh wow, that's actually an interesting proof, because I guess it's saying for every MA, M plus 1 A is also in the set. It's using that as a way to show that for every element there's some space between it and the least upper bound. Yet that space shouldn't exist because it is the least upper bound. It should be like almost no space between this value and all the members in the set, yet it maintains a distance with every single element, so that's not possible, which means that this M must exist. That's a pretty vague proof. Maybe my brain's just not working super well, but yeah, I guess that would make some sense. Yeah, I guess this least upper boundness does come into play, but not in a way that is as direct as I imagined. It's certainly a little bit strange. Yeah, and I guess in the other case you let A equals to 1, and then it would just have to be bounded, of course. So I guess in that case we also know that we also saw that theorem, or was it a corollary? Yeah, it's a corollary about this. So I guess we can use that result, right? There also exists unique, but we're not going to use the fact that it's unique. That won't be necessary, I think. Now, of course, I think here there was a theorem about if you have a natural, then you can represent it, certainly in terms of well, naturals in that base. Okay, perfect. Now we just need to show that there exists a non-repeating representation for this less than 1 value, which works. So let's just do that. But before we do that, let's compile. Okay, so I think we can demonstrate this with induction. If a present value has so if the sum needed to exist at a certain index is less than, okay, I think I'll just write it out. That's probably easier to do. But actually, it might be difficult because it's an infinite sum. So to peel off the individual elements directly might be a bit incorrect. But we do have this information. Right? Where it says where equality holds if and only if this is true for all I, etc. Yeah. Wait, what is this for? Hold on, what the heck? Okay, I guess this 3 is pretty useful, but this is only for this is only for repeating starting from the first index. Maybe from here I can start by way of contradiction, assuming there is some repeating decimal. Maybe I can do that. But I'm just a bit timid about breaking up this infinite summation, because it does actually have a definition, but it's not the one that it has this definition. So I think I would either have to use this or break it up, but I can't break it up, so because there's no proof that I can actually break it up. Oh, but I think there was an actual part that says that you can split off one of the terms from the infinite sum for the supremum, but I forgot where I saw it. Oh, it was right here. I'm dumb. Yeah, I think I can just use this directly. Oh, no, but it's not a part of the summation, I guess. Yeah, that's going to be a bit weird. Yeah, I have to work with the supremum definition somehow in such a case. I think I had some notes on this. I did do every single one of these questions already, but it was kind of on the bus, so, and it was a while ago, so I probably forgot how it even worked. So I would have to find it. Oh no, yeah, I did it by splitting the integral. Oh, sorry, not the integral, the sum up, which it's okay, I guess, but it's not great. Maybe I'll jot down a few notes and see if I can find anything interesting. Okay, let me just check in on It's just a supremum over the finite sums, right? Seems like that's what it is. Yeah, it's a supremum over the finite sums, or I guess partial sums. But it's a finite, you know, if it's a finite sum, I can well justify breaking things off. Okay. In that case, I might have something. I'm not 100% sure, but I have to tread carefully around this situation, honestly. Yeah, I think if I use exercise 2.8.5 and break up the supremum cleverly, but I'm not sure if that's a word, cleverly. I guess I can make this work, but it's not 100%, I guess. Oh, I forgot. I need to put negative exponents. I think this is actually quite reasonable, I guess. So first I will demonstrate this by proceeding with supreme roots. I think I can use this fact. Okay, I think that's reasonable. Okay, so I think this makes a lot of sense actually. That in fact this is an upper bound at least. What am I doing? I can just copy this. Are we allowed to use the geometric series formula? No, I guess we do have this. So since the repeating decimal is actually just p minus 1, it's probably just this. Oh, I should have just used this, I think. Made a mistake. Yeah, it seems like a pretty computation-heavy chapter, which I guess, I mean, it's real analysis, so it should be expected. Yeah, I think for finite series we can use the sum because they're using it here, so yeah, for finite series we're good. much. Now I need to do the geometric series formula. I'm such a noob at this, like honestly. I suck at doing any sort of computation. So I guess p minus 1 we can ignore for now. Is it? I think it's... okay, no, I guess I need to prove it. That's mildly irritating, I suppose. Okay, I can type the proof quickly. Yeah, that looks sort of right, but it's not really convincing. I don't know how to feel about this, honestly. Let's see, the spacing's on the back. Okay, so certainly switch it around like this. If I switch this around, okay, but how do I go about demonstrating that this value is actually, let's say, less than p times, oh sorry, p to the k, minus k minus 1. I suppose that would be the difficult part. Well, there's also, I guess this can sort of negate and cancel out with that one. It's a bit tricky. Did I screw up? that's a good point. I think maybe I screwed up at some point. Rather suspicious. Okay, let's try it, I think. Before being too pessimistic, it could be good to try it. So I mean, this is like p minus p times this, I guess, right? Because minus this is, well, I shouldn't have canceled it out. Gosh darn it. Or, yeah, I shouldn't have turned the minus sign there. Is this p times that? Yeah, it's just p. Okay, I'm such an idiot. Yeah, it's just p times this. My brain sucks sometimes. I don't understand myself. Yeah, I don't need the frac. And then here we know that this is equal to this, and this times p. Let's go back here. No, quit that. Okay, so this value is definitely less than, okay, let me just, oh, don't need this. Oh, what am I doing? To get familiar with when. Yeah, so this value is less than that. Wait, what was I trying to accomplish? Oh. Wait, what am I doing? I think this was useful actually. This is actually equal to the value m minus this. Like, I can sort of see it in my head, but it's not as precise. Since this is less than epsilon, then m minus this will be greater than, let's say, m minus epsilon, which means this would be greater than m, I think. Yeah, so, you know, that makes sense. Okay, I think that's a good enough demonstration that m must indeed be the supremum. I think that's the biggest part of the problem, once I was able to demonstrate that in fact these two values are equal. I think that's probably it. Seems like a pretty straightforward problem. Oh. Or, well, I guess I shouldn't say it's straightforward, because it took me such a long time to even think about. And if I'm honest, I'm not the most proud of this solution, I would say. So I suppose I can't really say things like that. Oh, wait, I made a mistake. Yeah. Yeah, I think this, even one part of this solution already took me quite a long time to write up, honestly, so I wonder what happens to the next part of this problem. Oh, okay, so you don't have to start with a 0 here. Okay, that seems straightforward enough. If there is a 0 in the leading digit, I think just show that not having that 0 produces an equivalent sum. There's nothing too crazy there, I think. And of course, if it's only the decimal portion, and you have a leading 0, I think you can use, it goes right here. I think you can use this. So yeah, that pretty much solves that problem. I think I'll type it up later, maybe. Yeah. I think the progress is too slow. I need to spend more time typing these things up. Otherwise, I won't get very far, if I'm being honest. But juggling this and my actual job is not too easy. I would say it's need to find a balance.